in this lecture, we are going to discuss about image compression. So, image compression model. The image compression system is composed of two distinct functional components, an encoder and a decoder. An encoder performs compression while decoder performs decompression. So encoder is used to remove the redundancies through a series of three independent operations. So I will explain this one later on. Both operations can be performed in a software, as in the case of web browsers and many commercial image editing programs, or in combination of hardware and firmware, as in the case of DVD players. So you have already known about that. There is a JPEG format which will compress the images, and there is a zip format that is also compression technique, a different kind of compression technique. So a codec is a device which performs both coding and decoding. So now this is an image compression model in which this the input f of x comma y is an original image, then there is a mapper, then there is a quantizer, then symbol encoder. These three components makes encoder. Finally, we will get a compressed data, and then there is a channel, and then there is a decoder, which consists symbol decoder corresponding to this symbol coder, and then there is an inverse mapper. And finally, we are going to get f hat x comma y. This f hat x comma y is a decompressed image. So now what is mapper? So f after this is an input image, this one is a mapper. So no interpixel redundancy. It transforms input data in a way that facilitates reduction of interpixel redundancies that we had already discussed. What is interpixel redundancies? It is a reversible process. It may or may not reduce the amount of data to represent images. Example, run length coding. In video application, mappers uses previous frames to remove temporal redundancies. Now next one is a quantizer. No psycho-visual redundancies. It is a non-reversible. As you know that it will quantize the values. So it will be a non-reversible process. It keeps irrelevant information out of the compressed representation. This operation is irreversible. It must omitted when an error-free compression is desired. So if you need an error-free compression, then you have to remove this block, this quantizer block. Since this is an irreversible process, so if you add this quantizer block, so you are going to get a lossy images. The visual quality of the output can vary from frame to frame as a function of image content. Now third one is symbol encoder. No coding redundancies. It is also a reversible process. Generate a fixed or variable length code to represent the quantizer output and maps the output in accordance with the code. So we had already discussed about the variable length coding, in which we know that how we are going to compress the data. So how to remove a coding redundancies. Shortest code words are assigned to the most frequently occurring quantizer output values. Thus, it minimizes the coding redundancy. So then, for example, any intensity that occurs more number of times, so we are going to assign a shortest code for that. In that way, we reduce the coding redundancies. It is a reversible. Upon its completion, the input image has been processed for the removal of all the three redundancies, that is interpixel redundancies, coding redundancies, and psychovisual redundancies. Now decoder is an opposite or of inverse of compression, so it follows inverse steps. So there is a symbol decoder and then there is a inverse mapper. Quantization result is irreversible loss. An inverse quantizer block is not included in the decoder block. As you know that quantization is irreversible process, so we cannot perform an inverse of step. If we are going for a lossless image compression, then we have to remove the quantizer block from the encoder block. Now compressions are two types. First one is a lossless or error-free compression. So as I have already discussed that in that case you do not have to put the compression quantizer. While there is also a lossy compression. In lossy compression there is an additional block as compared to the lossless compression, that is quantizer in the case of in the encoder block. So unlike the error-free approaches like lossy encoding is based on the concept of compromising the accuracy of the reconstructed image in exchange for increased compression. So that have a larger compression as compared to the lossless compression. So many lossy encoding techniques are capable of reproducing recognizable monochrome images from data that have compressed by more than 100 is to 1 ratio, and images that are virtually indistinguishable from the original at 10 is to 1 to 50 is to 1 ratio. Whereas in lossless compression, it is seldom to achieve more than 3 is to 1 compression ratio. So the principal difference between these two approaches is the presence or absence of quantizer block in the encoder. So in this video, we are going to discuss about lossy predictive. So this one is a lossy predictive coding model. This one is an input image. Then this is a quantizer block. Then this one is a symbol encoder. This one is a predictor. And after that, this symbol encoder, we are going to get a compressed sequence. And this compressed sequence will fed into a symbol decoder, and then there is a predictor, feedback predictor, and after that we are going to get a decompressed image. So in this case we have a predictor. With the help of this and error, we predict f dat dot f hat n. So if this f hat n is equal to this E dot n, the quantizer output, plus f hat n. So this f dot n, that the predictor input, is equal to the quantizer output, that is E dot n plus f hat n. This f hat n is subtracted from the original image is an error. So if we are going to subtract this fn minus f hat n, then it will give an error E of n. And when this E of n is passed through the quantizer, it quantized it, and we are going to get E dot n. So this error is mapped to another range of error with the help of quantizer. So that will compress it. So quantizer reduces the psycho-visual redundancies from the data. Now this error is sent to the symbol encoder that will encode this error into a variable length code. So finally we are going to get a compressed image. This quantization error will also add to the this one. This will also add to the previous prediction, that is f hat n, and that will act as input of the predictor. So f dot n is equal to E dot n plus f hat n. The error is added to the previous pixel prediction, and that we can get the input for the predictor. Now f hat n is equal to alpha f dot n minus 1. So based on the previous prediction, so f hat n is based on the previous prediction, and this one is a current prediction. sorry, this one is a current prediction, and this one is based on the previous prediction and error. As you know that f n minus 1 is e dot n minus 1 plus f hat n minus 1, and quantizer is defined as e dot n is equal to plus zeta for error is greater than 0 or minus zeta otherwise, where alpha is a prediction coefficient, normally its value is less than 1, and zeta is a positive constant. And same predictor is used in the decoder. So based on the previous decompressed image value, it will predict the current coefficient and defined as f dot n is equal to f hat n plus e dot n, and the difference of this is used to achieve the decompressed image or sequence. Since we perform a quantization, therefore the original image cannot be retrieved, hence it is called lossy compression. But its compression ratio is much higher as compared to lossless compression. That is the main advantage of this lossy predictive coding model. Then there are error-free compression. Error-free compression is generally composed of two relatively independent operations that reduce the interpixel redundancies and introduce a coding method to reduce the coding redundancies. So these are variable length coding, in which we are going to study about Huffman coding, then LZW coding, bit plane coding, and lossless predictive coding. So in the next lecture, we are going to discuss about variable length coding or Huffman coding.